All right, let's now take a look where we are. So last Thursday, I'm going to make a lecture video available to you. You can maybe take a look at that, maybe during the reading week. That'll be some nice background for you to know more about formal methods, verification, validation, etc. That's really about the motivation for this course. But today, we're going to start talking about a bridge controller after one more exercise from the math review lecture. Okay, we'll talk about it. And for your programming test, it's being graded. I'm hoping that I can release the result back to you because next week is the reading week, either towards the end of the reading week or maybe shortly after, maybe right after the reading week, maybe by the Tuesday class before the reading week, after the reading week. So because we also need to run some makeup tests during the reading week as well, so we better grade all of them together. But I'll keep you posted for sure. You're gonna receive the result and the feedback fairly soon. And your written test number 1, you may also want to start preparing for that. Let's look at a semester calendar to see where we are. And I can tell you the tentative plan. So the semester calendar is right here. Okay. So today we are here, lecture number 10, right? So we're going to start talking about the bridge controller, some background for today and also Thursday. And then I'm going to release your lab number 3, which is more like a continuation of the celebrity problem, just for you to get more exposure to it. Just one more lab, and then we get another new stuff in the lab number 4 later. I'll release that in time. And your written test number 1 will be the Wednesday right after the reading week. So I'm thinking that I'll try to give you guys some guide and also confirming the coverage for the test. Maybe no later than maybe that Monday over here. So at least you still got more than a week. But for sure, your written test number 1 is going to cover the math review lecture entirely. That's for sure. Okay. Also, the mathematical concept you actually learned from lab 1 and lab 2, very similar to what you actually study for programming test 1, just for the programming test. Except that it's going to be more like an E-class and multiple choice based. I'll give you some example question as well. I'll definitely confirm about all the format, all the coverage. Maybe about 13 around this day. By Thanksgiving Day, I'll try my best, by the end of the day. Okay. And I'm thinking that it would be very helpful if we can also host maybe some review session, maybe to go over the example test questions. You guys can also ask me questions. I'm thinking about tentatively it could be on this particular Friday during the reading week. So I can make it in person, and maybe you guys can come, and then we'll see, exactly. Or I can make it online. Either way, I personally prefer in person more, but we'll see. But I'm going to give you example questions. I'll host a review session before your written test 1. Hopefully you get prepared for that. But you definitely can start preparing already. The math review lecture, that's for sure. Maybe some part of the bridge controller as well. We'll see how much we can cover before the reading week. Okay. Okay, so I think that's about it. Right. Guys, any questions? Yes.
Along the release of the grade for the programming test, are you also going to release the question for the programming test?
No, I'm not going to release the question for the programming test. So I think if you believe there might be some errors in the grading, we have like a link for you to submit some regrading request, in which case the TA can take a look. If you really want to get some more like in-person feedback on maybe some parts of your test, you can drop by the office hour. We can talk about it.
Okay, because it's been 2 weeks ago, I even forget what's on the questions.
Yeah, well, you can always come to me, towards the end of the semester even. You can just drop by and then we can maybe go over very quickly. May not be very in-depth.
How detailed is the feedback going to be in the class? So for example, does that say, So
how about this? Once you see the feedback, you will see.
Okay,
yeah. Mm-hmm. All right. All right, guys, any other questions about the course? Yes?
Sorry, I just arrived about the second point. Was last Thursday's class lecture video already released?
Oh, not yet. I'm going to make it available very soon. But that one's going to be pretty light, just about some background information. Okay, yeah. All right. All right, if you're good. Okay, why don't we go over one more case study about math review, and then we can go on to the bridge controller, which is going to sustain us almost until the last class of the semester. It's a very big case study that will be worth our attention for the rest of the term. Okay, let's now talk about one more example. This one actually is quite interesting. That may not be something you have thought about before, but it's actually quite a straightforward idea to think about. Okay, let's talk about arrays that you learned maybe from the C course 2031 or 2032, or maybe the Java course, Java array. Okay, so now we talk about an array, let's say string array. You know, that's how you declare in Java. And then how we can formulate the array as a partial function. Okay, so let's talk about this idea quickly. And then we'll talk about like a different modeling choices as well. Okay, let's see here. Let's say you got a Java array, you got names, we got Alan, Mark, and Tom, right? We know pretty well indices 0, 1, and 2, right? So this is just one way to initialize the array. Let's take that as an example. So let's visualize this very quickly, and then I'll tell you why it can be thought of as a function, really. So think about we got names array, which is really referring to an array of size 3. So that means only 2 indices are valid. We got 0, 1, and 2, right? And each one of them has some element. For now, it's simply just a string. So we got, for example, Alan, and also Mark, and also Tom. So all these. Apparently, you can see there's 2 sets of value over here. So we got 0. Okay, let me make it thicker. We got 0, 1, and also 2. And we also got the string value Alan, Mark, and also Tom, right? You can think about when we're doing indexing of the array. For example, you might say names, index 0, index 1, index 2, right? And then you're able to get the corresponding elements in the array. Basically, every slot is storing at most 1 string value. Doesn't that sound familiar? Some concept, right? About function, right? So we are really talking about a function, right? So think about we can formulate the array as a partial function. Okay, so let's now write this down right here. Okay. So you can think about we got the names array, which is a member of the set of all possible partial function. So partial, we can justify that in just one moment. Let's say we got indices, right? We got 0, 1, and 2. So these are like domain values. So here you got choices. You can either say you want to get natural number or you can get integer. But since it's partial, so it's really going to be okay. So let me say integers, okay? So here I got integer and then partial function and then string, okay? So here this one tells us that the fact that it is partial, that means only certain indices are packable. Only certain indices are packable. Namely, 0 all the way up to the length of the array minus 1. We know that pretty well, right? And question for you, right? So let's talk about one more choice. So partial function is pretty straightforward. Given some index, if that's valid, you can find a corresponding value. Could be some string or could be none, right? So just as some reference. We learned about injective function, right? What does it really mean? When I say this declaration, if I say names is a partial injection, right? If you guys remember, injection is more about the domain value, right? And then over here, partial injection between the integer and the string, okay? What does it really mean? When I say names is actually a partial injection as opposed to just a partial function, what kind of extra constraint am I imposing on the array? Okay, think about it. So to answer this one properly, you want to somehow think about what's really the injective property, right? Injective property simply means if you got 2 distinct domain values, they cannot really map to the same range value. They should really map to 2 distinct values. Right? So how do we apply this mathematical concept to a programming array? Diego, is that what you're thinking about?
Sure. Yeah, so basically it would mean that 2 different indices of the array shouldn't be pointing to the same.
I agree. Or in other words, we're saying that array contains no duplicates, right? That's really something we actually, maybe in the first year, we can write a double loop to a nested loop to really decide. But mathematically, you can easily use the injective property to specify. Right? Let's write it down, okay? This will be the sorts of modeling decision you want to really keep in mind. Since we have learned about so many different choices you can opt for. So think about choosing each one of them may have some additional constraint or consequence you might have. So this means distinct indices map to distinct string. Strings. And in this context over here, indices are part of the domain. And the strings over here are part of the range. Okay, so we're really saying the array contains no duplicates. So that means no duplicates. Okay, just an aside. Okay, you can think about these are two modeling choices. Choosing which one really depends on what you really need. Yeah.
So for the bottom one, does that mean like literally if index 1 and index 2 are both named Mark, for example?
It will not be allowed, exactly. So I can make it more explicit. So let's say here, it's a good question. Let's now get it very explicit. If you opt for this particular choice, what does that mean? That means you are basically filtering out, you are disregarding an array like this, for example. Let's say we still got 0, 1, and 2. And maybe you got Alan here. And then you also got Alan here. And also, let's say we got Mark. Okay, so this is no longer allowed. Simply because you can see we got two indices over here, but they map to the same string values. It's not allowed anymore. Good? Okay. So on the slides, we actually got several different choices for us to think about. So let's have some very quick discussion. Okay, I just put on my notes over here. Okay, the first one. So let's say if we have the first one. So we already talked about array being injective. Okay, the second one. Okay, how about this one here? So I'll just use the bullet points from your slides. So we are now into bullet point number 3. What does it really mean when we actually got the names array? It's a member of, let's say, this function here. Okay. First of all, can you just tell me what that function really means? Do you remember what it is? It's partial for short, right? If you remember, there's a partial, and then we are also adding one more on the range side, right? It's a partial surjection, okay? Now, partial surjection definitely puts some extra constraint. What is that? Partial surjection. What does surjection really mean? That means the range should be the same as the second set, right? If you got a relation between S and T being surjective, it must be, the range must be exactly T, right? The second set. But what about here? How do we interpret that literally? Somehow, if you think about it, it is saying that the range of the names should be exactly equal to the second set, which would be the set of all integers, right? So somehow we're saying the array somehow will store all the possible integers, right? Is this feasible though, right? So there are two things over here, right? So if you think about the theoretical integer over here, it's definitely infinite. It's definitely not possible, right? Because you got minus infinity to plus infinity in theory, right? It's not possible, okay? So it's already infeasible. So this is not a valid modeling decision because it's not feasible. However, if we somehow modify that slightly, it may be okay. For example, you might say instead, if you say the names over here, let's say I still want a partial surjection over here. Maybe I would say partial surjection right here, the same as before, but now over here, I might just put, for example, I can define some carrier set, for example. I might just say int. Maybe this int here really corresponds to the 32 bits integer. If you got really enough memory, maybe you store all the possible integers in the array. Maybe that's possible, right? So this one here, this may be the 32 bits integer in Java. Basically a primitive type int, really. So in that way, it might be okay. Feasible if the memory allowed. All right, So that's kind of some consideration for you. But if you really use a Z, theoretical integer over here, it's definitely not feasible. It's just not infinite. Because when you talk about programming, it has to be finite to be stored in a computer. Okay? Okay, one more. Let me just put another one here. What about right here? So number 4 for your slide. Oh, by the way, it's slide number 36 from your math review, just in case you're wondering. So let's say we still got a surjection. But now I say A is a member of, let's say, partial surjection still. But now I put string. Let's say string is declared as a carrier set, like a string data type in Java. Okay? So think about this will be the set of all possible string. Right? So what this really means, similar, we are saying that somehow the array stores all the possible string values. That also sounds not feasible, right? Because for string, you can think about empty string of length 0, and maybe all the strings with length 1, all the string with length 2, all the way, right? So it's just too big a range for you to store, okay? So here we are saying the range of A over here will be all the possible string. Okay? Also, it's not feasible unless you really restrict to certain string value that's finite. Okay? All right, so number 5, the final one. Actually, the final one, number 5, I can just put a note over here. Number 5 here is really related to number 3. Okay? When we actually restrict the integer to be int data type. Okay? You can also refer to it. So it's related to number 3, about the int data type. But I think the most important lesson to learn from this case study here is, think about when we got array. You basically got domain as the indices and range as the value you're storing. Doesn't need to be a string, can be any value. And then you think about the injective, first of all, about partial and also partial injection. So these are the two valid choices that we just talked about, right? If you want to really make surjection, you have to make sure the second set here is really finite in order to be feasible. Okay? All right, any questions? That will be the last example I want to talk about for the math review. All good? Okay. So we are now completely done with the math review. So now we can move on to the case study, about refinements. Of course, part of the course name is really refinement. We're going to talk about refinement gradually. Okay. Okay. So we are now done with this. All right. Let me just show to you guys about where you can find the slides. Well, you should know. So let me close this one here. You will see that it's under the bridge controller here. Okay. So that's the slides I'm going to go over, but mostly I'm going to just focus on my iPad to really go over the example with you. So notice that this slide here is not yet complete. So there will be 3 models we have to talk about for the bridge controller. Initial model, refinement number 1, and refinement number 2. For now, I'm only putting the slides for the initial model. So if you really plan to print the slides out, maybe don't do that just yet. Maybe just maybe put that on your computer to look at. So whenever there's any updates, I'll let you know. But I think the initial model is going to take us a few weeks to really finish. There are many things we're going to learn from the initial model. Okay. All right, so that's where you can find the slides. And then let's now talk about this bridge controller example. Okay. Okay, let's see the list of things that we're going to learn. We're going to revisit the idea about requirements document. If you remember we got E description and also R description, right? So we'll talk about the requirements document for the bridge controller to see what the E descriptions are and R descriptions are. For every model that we're going to build, we're somehow going to reflect parts of the requirements documents. That's something we'll do. And we'll study what a refinement is. You can think about refinement in the most general sense. You're trying to fine-grain something even better. If I got some initial model there, it might be very coarse, not lots of details contained. And then I'm going to introduce maybe some refinement to make it a little bit better, containing more details. Okay, I'll talk about it just right after this. Just talk about some concept. And we're going to write formal specification. That's something you have been trained pretty well. So about two parts, about static, the context. We're going to see constant axiom theorems. That should be, context really the same, right? We're going to see in a different example. And also we're going to see the dynamic part, variables, invariants, events, guards, and actions. But this time, we're actually going to look into more about the design for the guards and the design for the invariants. We might give you something that might be problematic in the first place, and we're going to see how that problematic invariance might run into some failure in the proof obligation. And then we're going to see how we can fix it and then come back and reprove it. That's kind of the iterative process we want to see. Okay? That's really the value of using mathematics to do something useful for the verification. And then we're going to talk about proof obligation. So in this course, as I kind of hinted in day one, even though Rodin has a prover, but that one really requires lots of time to really get to learn about it. Since this course is only 12 weeks, we don't have the luxury of time to really learn about the prover. So I decided that, so this year, this term, we're only going to learn about how to discharge the proof obligation on paper on the slides. So that's something you just get to get used to for the written test and exam. And for Rodin, we don't have to worry about anything about prover. Okay. Proof obligation, and we're going to see in order to prove that one model is a refinement of another, there will be a series of proof obligation we have to discharge. And that's something we have to learn. Number one, the syntax of expressing the proof obligation itself. And number two, a certain way to discharge the proof obligation. We're going to learn something called sequent calculus. You might have seen something similar maybe in your 1090, but just the syntax you got to get used to. It's not difficult to really get used to it. We'll talk about it. Lots of examples to come. And then we're going to see how we can prove some properties. Namely, we're going to see how we can discharge safety property, like invariance. We got to make sure there's no clash, between the cards in the breach. That's one thing. And also, there's another property called deadlock freedom property. We want to make sure the system will always function. It's not going to run into a deadlock. So maybe from your operating system class, what does it really mean for the system deadlock? That means no party can actually make any progress. That's not good for us, right? So there's a way to actually formally prove about deadlock freedom. Okay, and for sequent calculus, that's the syntax we're going to learn. And also, there will be a series of inference rules. I think in total, I forgot the exact count, maybe about 20 or so inference rules that we'll have to study, right? Inference rule. But for the written test and also for the exam, you will be given the reference to the inference rule. So you don't really have to memorize them, just get yourself familiar. So just in case you want to refer to the details, you always got the PDF available to you during the test. But for the exam, you got to make sure you put a screenshot maybe on the data sheets. Okay? They will prove to be useful. And any example or questions I'll give to you in the test or in the exam, they should be solvable or provable using the inference rule that we cover in the course. So that one you can be rest assured. All right. So here I say recall, but this is only assuming that you have already seen the lecture, for the background. But that's okay. So I'll give you that video later. But let's talk about a very important concept, especially since we talk about refinement in this course. It's a concept called correct by construction. All right. Let's now see. You can go over the bullet points, right? It's quite a dense slide here, talking about many aspects. But let's now just talk about it on the iPad, right? I will develop from scratch. Okay, let's see what that really means. Okay. So correct by construction. So you can think about the construction here. We are really talking about construction of a series of models. The construction of a series of models. And of course, they're somehow related to each other. Okay. This will be a very typical pipeline of the model. Okay? So I simply use indices starting from 0 like an array. I got model 0, model 1, model 0, model 1, all the way to model n. Right? So in this particular case, we got from 0 to n, we got n plus 1 models. Right? Just a way to refer to them. So here I got n plus 1 models in general. You should get at least one model, but typically you should get at least two if you talk about refinements. Okay? Let's see how we can understand about this pipeline over here. But for our bridge controller example, we're going to see 3 models in total. we're going to see for the bridge controller, we're going to see M0 followed by M1 followed by M2. We're only going to see 3. But of course, if you build something else, you might need more than 3 models in the pipeline. But I think 3 will be good enough for us to see the ideas about refinements. Okay, let's see the very special thing. Let's see the beginning and the end to see why they're special. Let's start with the M0. Okay, M0 here is called the initial model. M0 over here. This is so-called the initial and most abstract model. Initial and most abstract model. Okay, so when I say abstract over here, abstract simply means containing the least amount of details. So maybe we only got 1 variable as opposed to 10 variables, just 1. Okay, so simple for us to consider. So that'll be containing the least. Okay, let me write properly. Least amount of details. And therefore, abstract will be the simplest. However, even given a model that's so simple, you can still prove something useful about the bridge controller. We'll see. Okay, simplest. Okay, and then okay, good. On the other hand, if we look at this one here, at the end, this will be the last, right? It will be symmetric. This will be the final, most concrete. Model. And concrete, most concrete in the sense that it's very close to the ultimate implementation. Maybe once you get a very last model there, maybe you got a series of maybe 10 different refinements. When you got to the 11th model, that'll be very close to maybe C code, etc. So you can easily turn the final model into some working implementation. So this will be the closest to the ultimate working implementation. For example, C code. We wouldn't see exactly like a C code in this course, but it's just ideally, right? If you look into that textbook, if you're ever interested, they do have some case study on that. But we don't quite need it for here. Okay. So we got the beginning and the end. All right, let's now take a look at the middle. Oh, just before I want to talk about one more thing. Okay, the reason that we really want to have a construction of a series of model is because you don't really want to do any verification or try to do mathematical proof on something that containing so many details. It's simply not possible, just too complex. Okay, so what we want to talk about here, the reason that we want this approach is having a so-called, having a single so-called Superman module. Superman model. And verify it is not feasible. Imagine that I simply develop a single class containing 1,000 or 2,000 lines of code and try to verify that directly. That's not feasible. Instead, what we want to do is we want to start with something very simple, covering only one aspect or some aspects of what we want to verify. And then we gradually add more and more property into individual models down the pipeline and then try to do it bits by bits. Okay? So instead, we distribute properties into different models. Okay, so each model will only get some amount of the properties to verify, so it's much more feasible in that way. Okay, let's take a look at just this part here. Okay, let's say somewhere in the middle we got MI and MJ, right? Just basically some adjacent models. MI, MJ could be M2, M3, could be M0 and 1, well, in general. Okay, let's take a look at this one here. Let's say something about it. So this one here, we say that MI, you can think about MI is more like a predecessor of MJ. And MJ is like a successor of MI, right? You can think of it that way. It's more like a linked list, linked node idea, right? So we say that, number one, MI is more abstract. Then MJ, all right? And then also MJ is more concrete. Then MI, all right? So if you think about these two, okay? So think about MI and also MJ. So MI, or MI, also MJ and MJ, just relative, okay? Okay, let me see if I miss anything. So the idea would be, when you somehow want to show, over here, one more thing, to show that MJ is a refinement of MI. Because MJ that comes after MI is actually more concrete, so it got a little bit more details added. So we say MJ is supposed to be a refinement of MI. A list of proof obligations need to be discharged, which means you're going to prove them manually. It's more about how you write it, right? You can either say MJ is a refinement of MI. Alternatively, you can say MI is refined by MJ. You can also say that. Okay? So when you say MJ is a refinement of MI, alternatively, you can also say MI is refined by NJ. Okay, equally. Okay, just depends on how you say that. All right, quick recap. So when we say correct by construction, we really got a pipeline of models, right? So think about if we go this way, we're just adding concreteness of the model, adding more and more details. So if I go this direction over here, okay, if I go for this direction, I'm just adding more and more details. More and more details added. The reason that it's called correct by construction goes like this. I start with the initial simplest model and prove that it is correct. It will satisfy a certain property. And then I go to maybe M1, the next one in the pipeline. I show that all the properties I want to prove in M1 also can be proved. And then I show that M1 is a refinement of M0. So now M0 and 1 are both correct, and then so on. When I get to the very last model here, once I also show that it's a refinement of the previous model, and then I can be sure this one here, that's very close to the ultimate implementation, is also correct. So it's really correct by construction. You basically keep adding details to different models. Okay? So you will be amazed. For the very first model we're going to see a little bit today, incredibly simple, just one variable for the bridge controller, because we're only focusing on one aspect, or one requirements we're going to see. All right, any question about this diagram here? All right, it's just more like an overview about what we're going to do. Okay, let's go over maybe some slides, some bullet points, and then we can take a short break, right? And then we can talk a little bit more about the bridge controller itself, technically, after the break. Okay, good. State space of a model. Okay, this one here. Okay, let's talk about this one here a bit. Okay, So what do we really mean by the state space? That means all the possible values you can actually combine together, given the variables and also declaration and typing constraint. Let's go over some example. Let's do this one here. Okay. So state space. Okay. So when we talk about the state space of some model, first of all, you can think about the more concrete the model, the larger the state space. If the concreteness of the model is increasing, that means we are getting to the end of the pipeline. Will mean the state space size is also going to increase. Okay, that's something to say right away. Okay, let's see some example here. Well, before that, let's see the definition. So whenever we say as the state space of a model is simply going to be all possible valuations or all the possible combination of the values. All possible combination of the values. Of what? It's going to include the constants and also variables. Right? We're going to use maybe your lab 1 example, just bank account, just to see some idea. Right? It's going to include both the constant and also variables. And subject to some constraint. And for the constraint over here, we talk about two kinds of constraint. Okay? One is the typing constraint. Maybe I'll declare a variable to be of natural number. In that case, I'm only including from 0, 1, 2, 3, 4, all the way onwards. If I declare a variable to be positive natural number, then I'm excluding 0, etc. Right? Typing constraint. But number 2 is actually more fundamental. It's about invariance you declare on the variables. It certainly makes a difference when I declare a variable to be a partial function versus partial injection. We know that partial injection is a strictly smaller set, as we talk in the math review. Right? So these two things will decide how large the state space is. Typing constraint and also invariance. Okay? Let's see one example here. Let's say we have our bank system here, just simplified version. Let's say we got two constants. We got C and also we got L. Okay? So let's say we got C here and we got L here. C and L. Okay? So one is the credit limits and the other one is more about the maximum balance you can have in the account. Okay? So let's say these are the two. Okay? So both of them are positive natural number, N1 and N1. Okay? And then we have another, we also got variable. So let's say we got accounts, which is a partial function between the string and also integer. Okay, between string and integer, sorry. String and integer. So here, typing constraint simply means we declare its type. Right? So at least we got something to start with. And then we also got some invariant property. Okay, you can think about this one here is invariance. So this one here is our invariance. That one further constraint about how the accounts can somehow be created according to C and L. Right? You can see the C here is used as more like a lower bound, and L here is more like an upper bound. Pretty much like what you learned, what you did in lab number 1. Okay? Let's just see some example. So we just say give some example configuration. So we're going to give some combination of these two constant and the variable. Okay? Let's say initial configuration. So let's see over here. So if we say the very initial configuration, let's start in this sequence. Let's say C and then L and then accounts. Okay? So it's going to be a triple. Right? C can be, let's say, 10,000. And maybe L can be maybe 20,000. And in the beginning, maybe the bank is simply just empty. I can put an empty set. Okay? You can think about this will be the C, and this will be the L. So that means every account can only go down to minus 10,000, but can go up to plus 20,000, right? And then empty bank. Okay, that's initial. And then I can just get another one here. Let's say we got configuration 1. Let's say somewhere in the beginning, somewhere in the middle of the system. I can still have the C and L the same, but now I have some account there, right? Over here, I can say bill maps to 5,000. Okay? And you can see that this one here satisfies the invariance. So this one here satisfies both the typing constraint because it's a partial function, right? It's a function between string and also integer. It's a function with only one order pair. And it also satisfies the invariance because you can see the account balance there. 5,000 is actually in between minus this and plus this, right? It's valid. And invariance. Okay, one more observation. Why is it so important to also consider the invariance right here? You can really kind of imagine, even with the invariance over here, the number of possible combinations of all the constant and also variables over here is very big. It's basically infinite, right? However, without the invariance, you will actually allow certain configuration that you simply don't want. Okay, let's see just one example. Okay, let's say, what if there is no invariance? If we don't have the invariance, let's say if we somehow got rid of this, that means we're only relying on the typing constraint. In that way, this particular C2 configuration would be allowed. So I can say C2 over here. So I still got, let's say, 10,000. I still have 20,000. And then here, I may allow the same account owner bill, but now it might be somehow go way below the credit limits, right? Maybe minus 5 million, for example. That will actually be allowed. But this one here shouldn't be allowed because it simply doesn't really satisfy the property, desired property for the bank. So this one should not be allowed. But invariant doesn't really say that. All right. Let's now just summarize by one more question, and then we'll take a short break, right? So somehow, how large exactly? So let's now try to use the set comprehension notation to see. So you can think about the state space. Basically, it's going to be a set of, we're going to have the variable and also constant list, depending on how many you have, right? If you got 3, it's going to be a triple. If you got 4, it's going to be a 4 tuple, right? The list of variables and constant, such that the typing constraint and the invariant should be satisfied. Okay? So we got the typing constraint over here, and also we got invariance over here. Both of them should be satisfied. Okay? So that means the typing constraint and also the invariance must be satisfied. Okay, both of them. And what's the cardinality of this particular set? I would say, realistically, for any example you want to kind of model the real life problem, the state space most likely will be infinite. You got so many variables, the combinatorial explosion is actually going to make it very difficult, right? So it's going to be infinite. So this is going to be very easily infinite. It's something called combinatorial explosion. I'm just running out of space, but you will see the term also spelled out on the slides, right? Combinatorial explosion, okay? However, luckily, for this course, since we are doing more like a paper proof, even though the system might be infinite, but when we actually generate the proof obligation, we don't have to worry about the sets that's involved being infinite. We just do apply inference rule. That's all we got to do. That's really the advantage of theorem approach. And for those of you who are in software engineering, so there's another follow-up course to this. I'll just make some context over here. Okay, 4315. Okay. So the state space being too large to really verify is really the bottleneck. So it's going to be the bottleneck of something called model checking. You don't have to worry about this term here for this course. Model checking is only the subject for 4315 when you get there, right? So when you do model checking, it's going to be a different approach compared with this course. For this course, we just do mathematical proof, in which case we don't have to worry about the state space being too large or even infinite. But in 4315, you have to worry about. Okay? We got different technique to actually resolve it. All right, so the takeaway from this page before we take a break is to really understand about what a state space is. Okay? And then we're going to see that when we do refinements, we are gradually increasing the state space. But when we start with something very small, very simple, and then we gradually add in the complexity. Right? Just understand about how you can exemplify some state space, and also know that this is conceptually the set comprehension. We can build a state space. That's all you need to know. All right? Any questions? Okay? All right. Question before we take a break.
For your set notation at the bottom, what are you writing on the left? The car cost loss?
Which one?
Yeah, so for your set notation for the state space,
Mm-hmm.
what are you writing on the left?
It's more like a list of variables and constant. For example, here you can see I got a list of the constants and also variables.
Okay.
Yeah. So basically, I got a enumeration of the constants and also variables that's declared in the model. And then on the right-hand side, any value that's going to satisfy the typing constraint and also the invariance, their value should be included. So I'm considering all the combinations.
Okay.
And of course, the combination is going to be very huge set to be considered. So that's why we said it's not the way to go if you want to do things like a model checking.
General definition. So if you write a bracket, like in this case, it's like CL account.
Yeah, CL account is only for this particular example.
Yeah,
but here I'm just making it more general. Just say it's going to be a list of all the variables and constant declared.
All right.
Yeah, good. All right, why don't we take a short break by taking attendance. All right, so before the break, we basically went over slide number 4, just about state space. Okay, and the term that I mentioned about combinatorial explosion. Okay, just for your knowledge, right? Whenever you talk about the state space, but too large for you to really verify. So that's called combinatorial explosion. And let's now get to the bridge controller. Okay, a little bit more. We're gradually moving towards the background. Okay, getting there. So we walk through the development process for the bridge controller. So basically, it's going to be a bridge regulating cars on the one-way bridge. We'll see exactly how to build it. Well, partially. And it's going to be a reactive system, meaning that there will be many parties working together. Maybe traffic lights, maybe sensors, and maybe the cards, different parties. Reactive. Reactive also means the system should always run. There should not be a scenario where everybody is simply stopping, like a deadlock situation. So one of the important property for a reactive system is also about deadlock freedom. Okay, that's something we'll see as well. And sensors, actuators, and the roadmap will be, we're going to go over the requirements document today about bridge controller. It's actually a very small document. We just go over them very quickly, just a few, less than 10 descriptions we got to go over. And also, we're going to just some overview about a refinement strategy. I'll just kind of mention which model is going to cover which aspects for the requirements. And we got initial abstract model. We're going to start with that today, and then we're going to sustain. We're going to go for that for a few weeks. And we got different refinements. I think we're only going to cover initial model, first refinement, and second refinements. We're not going to cover the third refinements. Hello. Thank you. Okay. All right, so there are going to be two concepts over there. There's going to be something called island and also something called mainland. So I thought maybe Toronto Island might be the best analogy for us. Think about we got an island in Toronto and also we got a Toronto Island. Right? The downtown Toronto is the mainland and also the island Toronto. And then let's say hypothetically we somehow want to build a bridge between the two sides. We can see how to do that. Okay? It's more like an engineering problem for us to think about. Okay? So let's go over the E description and R description, okay, quickly. And if you recall, what's the definition for E description? E description is going to be the constraint or assumption we make about the working environments. It's not really something we're going to prove or something, just assume that's the case. On the other hand, let me just go to the next page. About R description is really the functionality we'd like to establish, something we'd like to prove, right? Just remember the difference between E and R, okay? Let's take a look, okay? The green ones are the E description, and the red ones are the R description, right? We got all these. So in total, only 8, okay? So let's see this. So constraint number 1, about environments. The system, okay, I'll make it a little bit bigger. The system is equipped with 2 traffic lights with 2 colors, green and red, okay? So we basically talk about 2 traffic lights. So this could be a diagram you can think about. So we got mainland on the one end, and also we got island on the other end. And also we got 1 traffic light and the other traffic light. Each one of them only got, just got red and green. No ambient light, okay? Just red and green. And then we got a bridge. And a bridge is supposed to be only one way. It should be either going from mainland to island, or it should only go from island to mainland. That's actually specifying one of the requirements. Okay. Okay, so that's E description number 1, and also traffic light control the entrance to the bridge at both ends of it. So the traffic lights of entrance for both ends. That simply means one controlling if you want to go from mainland to the island, and also another one controlling from island to the mainland. Right. So these are the 2. And this environment constraint is also very important. The cars are not supposed to pass the red lights. So we are making some very important assumption. We're assuming that if, for example, there is a red light right here, then the car is going to obey the red lights. They are not going to go past. If we cannot make this assumption here, the model is going to become much more complex to really prove about the safety property. So that's more just an assumption we're making. All right. So this one here. This is very important assumption. In order to prove the safety property, as we'll see. So without this particular assumption, we simply don't know whether the red light or green light is going to have any effect on the cars going to the bridge. Okay, next one. And we also got 4 sensors, okay? There'll be 1 sensor here, 1 sensor here, 1 sensor here, and 1 sensor here. Just 4 different sensors. But this is really the refinement we wouldn't cover by the end of the semester. But there's something just to let you know. There's also environment constraint we can cover as well. But not, we don't have time for that, just for this semester. And then we got also more constraint about the sensor. It's going to detect the presence of a car, entering, and etc. Just about sensors, okay? So let me just, that's about the environment constraint. Let's see the functional property as well. The system is controlling car bridge connecting the mainland to the island. Okay, so that means this is the bridge, right? Connecting the mainland to the island, okay, like that. And then we got a number of cars. This is important. The number of cars on the bridge and the island is limited, okay? There will be certain cars in the bridge. There will be certain cars in the island. So think about the star plus the star star. Somehow should be subject to some constraint. For example, D. That's something we'll see, okay? We'll see exactly. And then the bridge is one way. That's very important, okay? You should not have car going this way and going this way at the same time. You should not have. So that's about all the 8 requirement, all the 8 descriptions we have, right? Remember we talked about correct by construction. That means you're not going to have a single Superman model to reflect all the constraint over here. We're going to distribute the properties or constraint into different models. Okay, so let me just show to you. Okay, for model 0, which we're going to start introducing today. So requirements number 2. Okay, let me use this one here. So requirements number 2 is going to be covered just by M0. So for our initial model, we are only going to focus on requirements number 2, nothing else, only that one there. But even for that one there, we can already prove some interesting property about the bridge controller. Okay, so M0 is this, and then requirements 1 and 2. Sorry, requirements 1 and 3, these two. Okay, this one here, and this one here. That one is going to be addressed by model 1. You can think about once we are able to prove things about requirements number 2, we're going to add another 2 functional property to cover in M1. So once M1 itself is proved, then we will be able to effectively cover all the 3 functional requirements. Right? We go gradually. We start from 2 and then add in 1 and 3 gradually. Question?
In the scope of this course, are we able to distinguish the environment and the requirement, or are they going to be given?
In this course, of course, you might be given sometimes, but if you're given environments, you're somehow supposed to encode them as maybe constraints, like an invariance or axiom in your model.
Yeah, so we don't need to tell, like, we are not going in a situation where there's no, you just get a bunch of requirements that we don't know whether it's environment or requirement.
Well, of course, sometimes you may have to decide whether the requirements is actually either E description or R description. You have to decide, right? But mostly you'll be given.
Okay.
Yeah, at least for the bridge controller example. So these are given, for sure. Yeah, you got to decide how to formulate them in the model, right? All right, so we got M0, M1. Okay, what about M2 and M3, right? So when we get to the second refinements, so let me put it here. Environment constraint 1, 2, and 3 is going to be covered by M2. You can think about when we get to M2, we are basically going to worry about traffic lights. Okay, that's really the main detail we're adding to M2. And the one that we are not going to be able to cover in this course will be the sensors. So that'll be M3. Right, you can see each model here, M0 all the way to M3, each one of them will cover some disjoint subset of the properties or the descriptions. Okay, so that's something we're going to look out for. All right, so we're going to look at all these, constantly, so you don't have to worry. Okay. And so one more thing. So this is the only one, the only requirements to focus on the initial model. That's the only one. All right. Okay. All right. Let's now go back to the slides. So we went over the E and R description, and that's a diagram we just went over. Let's now talk about the very initial model. Okay. And you will see also this slide here just about the distribution, of the different E and R description, which I just talked about, right? But for today, for now, we're only going to focus on just the very first one, requirements number 2, just about the number of cards being limited. We're going to see exactly how to limit that. Okay, M0. Okay. And for M0 here, before I show you the diagram, let's see what kind of abstraction we are adopting for M0. What kind of details are we trying to filter out? Okay. Okay, so in M0 here, we are not going to consider the bridge. That's kind of interesting. We are talking about bridge controller, but in the very first initial model, we don't even consider the bridge. The bridge is not even there. Okay. We don't consider traffic lights, and we don't consider sensors. Okay, so only requirement number 2. Just about the cards being limited. Okay, we'll get there. So some analogy. So think about you're really trying to look at a bridge controller and a bridge island mainland from some very high sky over there. So you cannot really even see the bridge. So the island and also the bridge somehow are more like a compound. You just cannot see it. So this is a diagram you want to get used to. Okay. this is a very important diagram right here, right? So let's say I'm trying to look at the construction from some very high in the sky. I got mainland over here. However, the bridge, since I'm staying so high, I cannot even see the bridge. Okay? I'm only seeing island and bridge altogether as a compound. Okay? And let's see how we can understand this initial abstraction. Okay, let's see. Okay. So first of all, let's now bridge and island. In this initial model, consider them as not separable. That's single units. Not separable. Okay, let's see one concrete example. Let's say if I actually got island here, let's say this is the island. And this part here is the mainland. Okay. Let's say if I do have a bridge in between. Let's say, for example, I may have maybe 3 cards on the bridge. Okay. Let's say 1, 2, and 3. So 3 cards on the bridge. Let's say I got already 100 cards in the island. Okay? But as far as M0 is concerned, we are looking at this as a compound. Think about this part over here, the bridge and the island as a single compound right here. So this one tells you that the number of cards, which we call n, you will see that later, is a variable, is simply going to be 100 plus 3. So this part here is from the island. And this part here is from the bridge. But we don't distinguish between them. So we talk about 103. That's the number. Okay? We don't have to worry about whether the card is in the island or in the bridge, just in the compound. Okay? So this is a compound over here, and we're going to use the variable n to denote that. It's going to be the number of cards in the island and the bridge. And in the slides, we call this the island bridge compound. Okay, right here. Okay, let's see if I missed anything. Okay. Okay, so that's just about conceptual, right? Just remember the abstraction we have for M0. No distinction between island and the bridge. Okay. Okay, awesome. Okay, let's see some decoration of the model. Okay, I'll show you directly right here. Okay, so to remember, we are addressing requirement number 2. So we got the static part, we got the dynamic part, right? That's something you kind of used to, right? Let's say we got some constant D. Constant D will be the maximum number of cards. This will be the maximum number of cards in the island and the bridge altogether. So you can think about if I have currently n cards right here. N may increase and decrease its value, throughout the course of the system. But that should be upper bounded by the D. Should be less than or equal to D. Okay? So n here is the current number of cards. And the D here is the maximum you can ever have. Okay? You might be wondering, what about mainland? Somehow it's unspecified for this initial model. We simply don't care. So you can think about it as unspecified or it's simply unbounded. Okay? But I'll put it down explicitly. For the mainland, how many cards is really there? We don't care. The number of cards is either you can say it's unspecified or it's simply unbounded. But we don't really declare any variable to denote that. We don't have to. Okay? And we say that the D here can be just a natural number. including the value of 0, right? So you can think about some theorem you can prove right away if you want to. So you can know that D here is larger than or equal to 0. That's a maximum. So maximum could be just 0, theoretically. Okay, so N here is going to be the number of cars, right? You can think about N is right here. The N here. So for now, we got 2 invariants. Okay? So we got typing constraint. Question? Yeah. You mean the D here?
Yeah.
Yeah, it's a natural number, so it can be larger than or equal to 0.
Oh, larger than or equal. I heard like just maximum number can be 2.
Yeah, so you can think about it in this way. So D here itself is a constant, but we don't really specify what that constant is. So we just say that it can be any constant starting from 0, 1, 2, 3. In the case where D happens to be 0, in that way we are not allowing any car to be on the bridge and the island. In the case where D is equal to 1, there's only one car that's allowed in either the bridge or the island, right? So, yeah. All right, so we got 2 invariant here. You can think about this first one here is more like the typing constraint. The N here is a natural number. Typing constraint. And the second one here is not really about type. It's just about some maybe desired property. Just make the state space more limited, right? So this is some desired property we want to satisfy. Okay? So this is some desired property, okay, that we want to maintain. Okay? So that's the initial model. Okay? Okay, let's now do one more thing, just to see how even some events. Okay, so if we go back to the slides, let's see what we have. So we got a static part, and also we got a dynamic part, right? That's something we just spoke about. And it is very important to know that invariance is namely this one here is the most important invariant. We got to make sure invariant will be, first of all, established when we first initialize the system. And number 2, invariance should be somehow preserved between the 2 different events. We'll see. Okay? So there are 2 events we're going to see in this initial model. Okay? It should be both established and also preserved and maintained. And maybe about, definitely after the reading week, maybe the second week after the reading week, we'll start seeing some proof obligation related to invariant preservation, also invariant establishment. That's something we'll see. Okay? All right, let's talk about state transitions. Okay? Let me just give you one example right away, right here, and then we'll go over some slide maybe on Thursday. Okay, just a few minutes. Okay, so here we got 2 events over here. So you want to also get yourself, familiar about the terms we're using. One event is called ML out. The other one is called ML in. Okay, let's talk about what these 2 events really mean. ML here stands for the mainland. And whenever you got ML out, that simply means a car has moved out of the island. So you can think about, this is ML out. So that means a car goes, we can think about leaves from the mainland to the island. Leaves the mainland. As far as M0 is concerned, when you actually leave the mainland, you simply go to the island and also bridge compound. So once you leave the mainland, you go into this compound, right? Symmetrically, you got another event called the MLN. MLN is right here, okay? So this one here means a car goes back to the mainland, goes into the mainland. A car returns back to the mainland. And you can see that we currently got just one single action right here. Okay? I will talk about the colon equal maybe a little bit more next time, right? But for now, you can think about what we learned from lab number 1. This simply means n is going to become n value plus 1. And this means n is going to become n value minus 1, right? Let's say, for example, if currently I have, let's say, 23 cards in the compound, let's say. If I actually got 23, okay? And then if I got one occurrence of ML out, it's going to increase from 23 to 24. If I actually got one occurrence of the MLN right here, it's going to decrease from 24 into 23, right? That's exactly the plus 1 and minus 1 you will see in the event, right? That's kind of easy to see, okay? What's really important here is there any guard for MLL and MLN according to the specification? Not at the moment, right? So if they're guardless, okay? Both events. MLL over here and also MLN over here, you see we had no guards. No guards simply means the events are enabled always. You can always expect the event to happen. Okay? That means always enabled. Okay? The design principle number 1. You should not have any events that simply will be enabled all the time. There should be certain constraints that would restrict about the availability for the events. So being guardless is definitely going to cause us trouble, which we'll see mathematically. Okay, so this is problematic, as we'll see. Okay, so just quick sketch. Let's say I have the D over here being 2. That means I got maximum number of cards in the islet and bridge compound over here being 2. Maximum 2 cards. And then initially n is simply 0, no cards in this compound, right? Given the design for MLL and MLN, am I actually going to run into trouble that's going to violate some invariance? In order to show that trouble, you have to give me a trace of the events, okay? So here is a question, and we're going to answer that on Thursday. Okay, let me write it down. Is there a trace of events that can lead to invariance violation? Can you see any possible event, trace that's going to lead to invariant violation? Just one example, right? For example, is it possible to really somehow keep allowing card into the islet and bridge compound so that the D here is actually not going to be upper bounded anymore? Okay, I'll sketch very quickly. Initially, n is simply equal to 0. If one occurrence of MLL occur, it's going to go from 0 to 1. And then another one occur, 1 to 2. Another one occur, it's going to be 2 to 3. Because all the ML out is actually enabled all the time. So there's no way you can stop it from happening. Right? So that's something we're going to make a little bit more visual and concrete on Thursday. All right? So we're going to finish a little bit earlier today. Thank you so much, and I will continue on Thursday. Thank you.